Okay, Unit 3, Worksheet 1, how much mass versus how many moles? So here we're going to be using the concept that a mole equals the atomic mass in grams of an element from the periodic table, and we're going to round these to the hundredths place. If you take a look at problem number 1, it says an old pre-1987 penny is nearly pure copper. If such a penny has a mass of 3.3 grams, how many moles of copper atoms would be in one penny? We can use this concept as a conversion factor to help us get our answer. So if you have 3.3 grams of copper atoms, I'm going to put this over 1. And then since I'm beginning with grams of copper here, you want that unit to follow you down here onto the diagonal so that you can cancel it. And we are converting to moles of copper. Just so you know, moles can be abbreviated MOL. You can drop the E off at the end if you wish. The number 1 goes next to moles, so I put the number 1 here on the top. The number that goes here is from the periodic table. It's that mass of copper, which is 63.55. 30.3 divided by 63.55 is going to be 0.052 moles of copper. Over here you had 2 significant figures. The one has infinite sig figs. This is 4, so you want 2 sig figs in your final answer. If you wanted to write this in scientific notation, you could write it as 5.2 times 10 to the negative 2 moles of copper. That's equivalent. That would totally be acceptable. You do number 2. It is just like this. You're simply using iron. Let's go to number 3. A raindrop has a mass of 0.050 grams. How many moles of water does the raindrop contain? So in number 1, we just did a single element, but in number 3, we're doing a compound. So here we're going to put this over 1. Since grams of water is your unit that you're beginning with, you want to have that unit on the diagonal, because you need to cancel this unit. We're going to moles. The number that goes here is from the periodic table, but we're going to have to add 2 hydrogens to 1 oxygen. If you look at hydrogen, hydrogen is 1.01, so I'm going to multiply that by 2, and then I'm going to add that to an oxygen, which is 16. Add all this together, you're going to get 18.02 grams. So this is going to be 0.050 divided by 18.02, or you could take this times 1 divided by 18.02. It doesn't matter, you'll get the same thing in the end. You're going to end up with 0.0028 moles of water. You started with 2 significant figures here. The one is infinite sig figs. This has 4 sig figs, so that's why we're ending with 2 sig figs over here. If you wanted to write this as 2.8 times 10 to the negative 3rd moles of water, you can. In standard scientific notation, it's the exact same thing. Let's turn the page. Let's take a look at number 4. Number 4 says what mass of water, so we're going to solve for grams, would you need to have 15 moles of water? So put moles of water over 1. Since you're beginning with this unit, moles of water, put it on the diagonal. And then you're going to grams, so put that up on the top. The number 1 goes next to moles, so it's here. The number that goes here was from the periodic table. It's the mass of water. We figured it out in the previous problem. It was 18.02. So you're going to take 15.0 times 18.02. I'm going to end up with 3 significant figures because you started with 3 sig figs here. This is 4 sig figs. The number 1 is exact, so it has infinite sig figs. 270 with a decimal point on the end is 3 sig figs. That's 270 grams of water, or 2.70 times 10 to the 2nd grams of water would also be acceptable. Now, number 5, you're going to do, number 5 is just like number 3. Number 6, you will do, number 6 is just like number 4. Number 7, you will do. Number 8A, you will do. I will do 8B. many moles of hydrogen atoms are in a sample of ammonia? Okay, so since you also know that a mole is equal to 6.022 times 10 to the 23rd things, those things may be atoms, molecules, or formula units. So we use atoms when we have like a single type of element. Molecules are molecular compounds. They're made of nonmetals. Formula units we typically use with ionic compounds when there's cations and anions. For 8b, you have 0.044 moles of ammonia from 8a. So when you do 8a, if you get this answer, that's how you know you did it right. We're going to put this over 1. Moles of ammonia is here. We're going to put moles of ammonia on the diagonal because we want to cancel that unit. And we're going to put 6.0, I'm sorry, not yet. We're going to moles of hydrogen atoms. If you look within this compound, you have 1 nitrogen and 3 hydrogens. So the ratio that you can write for ammonia, 2 of them, would be that in 1 mole of ammonia, you have 1 mole of nitrogen, or in 1 mole of ammonia, you have 3 moles of hydrogen. So since they're asking me for moles of hydrogen atoms, you would use this second ratio. So in 1 mole of NH3, I have 3 moles of hydrogen, and this is 0.13 moles of hydrogen. You have 2 sig figs here. These are exact. You have 2 sig figs here. Okay? So now you're going to use this concept. When you do number 9b, 9b is just like 8b in terms of the setup. You're going to do a ratio within the compound. You're also going to do number 10 and number 11 for homework, and you can check your answers on the last page. Okay? You want to read Unit 3, Reading 1, the origin of the mole concept. And I jumped the gun a little bit. We're not using this yet, but we will get there. So when you do Unit 3, Reading 2, how is Avogadro's number determined? That is when this will appear.